Hello students, good evening. So myself Krishna Kant, I'm the faculty at the Gate Academy. So we all know today we are going to discuss some concepts regarding communication systems. So the topic of today's discussion is digital communication. So we all know that our world is moving towards digital. Okay, so are you there? Is my voice audible? Please, there is a box, you can comment there. Okay, you can share your views. So please tell me, am I audible? Good. So we are going to start the concept today. The topic of today's discussion is digital communication. So before starting the class, I would just like to tell you that I would just like to ask you some questions. So why this world is moving towards digital? So what is the main advantage of digital communication? Please share your views on this. Please answer the question. Why we need digital communication? Why all the devices, all the analog devices are converted to digital? What is the advantage you are going to get for that? Hello, hello, Mohammed. Please share your views. So question is why? What is the advantage of digital communication? See students, the main advantage of this YouTube live or these type of classes are if we are teaching in a classroom where there are 200 or 150 to 200 students, some good students can't ask their doubts because of stage fear and all. So here we have that advantage, right? So you can freely ask whatever doubts you have. Okay, that's the main reason, main advantage of this YouTube live sessions, so that you can easily ask your doubts. So if how much interaction you are keeping, that much good our class will be. So please try to be typing it, so it will be interesting, so that your use you will tell. So what is the drawback of that? Is your use correct or not? There will be some sort of interaction to make it much more efficient. Very good. One of the student has answered, that is efficient, easy to handle, cheap. Good. We'll see, this is the efficient one. So we all know that whenever I'm speaking to someone, or so what will happen? The information, is it in the form of digital or is it in the form of analog? Whenever you're speaking to someone or whenever you are talking, is the information that you are giving, is it in the form of analog or digital? Digital. Now Ghosh is telling, yeah, analog. Very good. So whenever we are speaking, we'll be speaking for every time instant, na? So that is called continuous. That's called analog. So if you are here, if you are somewhere here, you are speaking, and if a electronic device is converting all your voice variations to some electrical voltage, so this signal is called to be a what? Analog signal. This is an analog signal. The value is defined for every instant of time, continuous time and analog signal. So when you want to transmit this information, that is the point where we got our communication system. Yes or no? The main aim of communication system is what? To transfer information from one place to another place. So we have studied this communication in analog communication part. I think that you all know that in analog communication, we'll be transmitting information in for every time. This information is transmitted and it is received. So here there will be some speaker or something. So that here there will be some other person who will be listening to the information spoke here. Here we'll use a simple device which is called a mic. So what mic will do? Mic will convert voice variations to electrical. After receiving, it is converted to, so this speaker will be converting this electrical signal to what? Physical signal, that is voice. So this is the overall task done by the communication system. So can you tell me what is the drawback of analog communication? What is the main problem of analog communication? What is the main drawback of analog communication system? So what is the effect whenever we implement it using a circuit? What is the effect we are experiencing? Please share your views. What is the drawback of analog communication? Noise. Very good, very good. So the main effect of analog communication system is what? Noise. So noise, we have studied in noise analysis and all. So because of some room temperature, if you see V equal to IR, Ohm's law. So whenever you study Ohm's law, na, V equal to IR is defined only at constant temperature, but temperature of a room varies, na. So because of these variations, the resistance will vary, so that voltage will vary. So whenever you're transmitting this analog information is affected with what? Is affected, this analog information is received, but there is some drawback of the received signal. That is what? Some noise will be added to this. So here we cannot eliminate the noise. Why? Because whenever you are speaking, the signal is for every time and the noise is also for every time. So noise effect is also for every time. And the main drawback of this is both are varying. Whenever you are speaking, na, the information is also varying, noise is also varying. So the basic idea of digital communication is this one only. When two things are varying, what you have to do? You have to make one thing as constant. So what we are going to do? We are going to convert this analog information to a series of bits, 1 0 1 0, something like that. So this idea, whenever signal is varying and noise is also varying, we cannot differentiate between the signal and noise because both are varying. Now this analog is converted to some constant voltages. That is called what? That is called digital signal. So instead of this analog signal, now I'm going to transmit this digital signal. So now I'll be receiving this digital signal by using some circuit and all. But this digital signal is also affected by noise because it is also voltage signal only, na? This will also be affected by noise for every time. But in digital, whenever we are speaking about binary ones and zeros, we have only two voltages. One is 5 volts, one is 0 volts, something like that. So whenever you have two voltages, here because of noise, what you are receiving, sir? You are receiving either 5.2 or 4.8. But in digital, these voltages are not at all defined. What are the two voltages defined? One is 5 volts, other is 0 volts. So as soon as 5.2 or 4.8 are received, what the receiver will do? Receiver will check. It is near to what? 5 volts, na? So it will be giving you 5 volts. And this 0.2 minus 0.2, those are also near to 0. So it is received as 0. Now what has happened, sir? In analog, the information is affected by noise. We cannot remove it because signal is also varying, noise is also varying. But if you see in digital, na, see here, all these random variations, noise is effectively eliminated because there is no voltage called 5.2 or 4.8. Only voltage we have is what? 5 volts. And this 5.2 is near to 5, na? So that is why it is taken as 5. This is the main reason why all the devices are converted to what? Digital communication, digital devices. So in this class, we are going to see how we can convert this analog information to digital. Very simple. Okay. Very good noise. So in this overall class, what we are going to do, how this analog signal is converted to digital series of ones and zeros, that is binary. So this is what we are going to do in this class. So any doubts till now? Any doubts? Please feel free to ask any doubts you have. Good. See here. So the sender and receiver is the same. Now also we are taking half duplex. He will be speaking, and here there is someone who is there to receive the information. This is not two-sided. This is just one-sided information. Okay. So what I am telling you, our system, our digital communication system must be able to what? Convert the analog signal, the signal which he spoke. If it is given to something called mic here, what mic will do? Mic will convert it to electrical voltage. So this electrical voltage has to be passed through some blocks. So this is passed through a channel, and after that it is given to a, and there will be a speaker here which he can be listen. So these are the various blocks which we need. So if you see once what are these blocks, so first what we have to do, we have to convert these time varying all the infinite voltages towards some finite voltage levels. So the first step of this is sampling. So after that we'll be quantizing, we'll be making all the infinite voltage levels to some finite, then we'll be converting it to binary using a encoder. This is a quantizer, this is a sampler. Once encoding is done, we'll be getting some bits. So we'll be converting it using threshold comparator is there here. Just try to understand this. I'll be explaining you about each and every block why we are using it. Okay. And after that we'll be decoding the signal. After that we'll be passing it through a integrator, that is a low pass filter. Okay. So see here the information is the same. The person is speaking something. All his voice variations are converted to what? Some electrical voltages. Okay. So what sampler will do? Sampler is a switch which will be opening and closing for every sampling time. It will be chopping the signal into some constant voltages. So if you see here, the voltage which you are going to get is this one. Something like this. Let us take 4 voltages. Okay, 4 levels. So this can be something like 4.2 and this can be something like 3.1. So this can be something like 2.1. This can be something like 0.9. After sampling, the continuous time signal is converted to what? Is converted to discrete time signal, NTS. 1, 2, 3, 4. First sample, second sample, third sample, fourth sample. After that, what we'll do? We'll be quantizing it. Quantizing means what, sir? The discrete voltage is reached to the nearest quantization level. We'll be designing some voltage levels. See here. So here, this is the x-axis which is time and this is the y-axis which is voltage. Sampler, what it will do? It will be chopping this x-axis into finite values. So how much samples you have to take depends on how much accuracy you need, and we have to also follow sampling theorem. The sampling frequency must be greater than or equal to twice the maximum message frequency to reconstruct the signal. You know that equation we got from sampling theorem. Okay. So what it will be doing? It will be chopping the signal into some voltages. After that, y-axis is infinite. It can have any voltage. Whenever infinite voltages are there, you cannot convert it into finite values of ones and zeros. So what we are doing, this quantizer will define the levels, how much levels you need. So this is done like this. So whenever quantizer is what? Quantizing into some voltages. So 4.2 will be getting you 4, 3.1 will give you 3, 2.1 give you 2, 0.9 will give you 1. 4, 3, 2, 1. So encoder, what encoder will do? Encoder will be converting these quantizer samples to what? Series of ones and zeros. So encoder depends on how much bit you are using. See, we have 4 voltage levels to encode. So you have to represent 4 numbers. How many bits you require? If you have only one bit, you can generate 2 numbers. One is bit 0 and other is bit 1. So if you have 4 digit, two bits, you can generate how many numbers, sir? four numbers. Those are what? 0, 0, 0, 1, 1, 0, 1, 1. Luckily, we have 4 voltage here. So encoder must need how many bits? 2 bits. So the n here is what? N equal to 2. How it is doing? See here. For encoder, 0, 0 will be encoded to some 4 volts. Okay, let us start with 1, 1. 1, 1 will encode it to 4 volts. So 1, 0 will encode to 3 volts. So 2 volts will be encoded to 0, 1, and 0, 0 will be encoded to 1 volt. This is called the mapping table of encoder. Whatever table you are using, the same table must be used in the decoder. So what you will get, sir? For 4 volts, you will be getting what? Encoder is converting 4 volts to what? 1, 1. It means 1, 1 you will get. 3 volts, what you will get? 1, 0 you will get. 2 volts you will get 0, 1, and 1 volt you will be getting 0, 0. So as soon as this is received here, all these bits are received. So now at the input of here, this will be affected by noise because of this channel. So what will happen? See here, bit 1 means what? Bit 1 means some 5 volts voltage for some TB duration. Yes or no? Bit duration. Answer for above questions are best reference books wanted for conceptual understanding and probabilistic method. Okay, we'll discuss in the last. I'll be giving you some guidance. What are the books you require and all. So first, focus on the present topic and try to understand why it has come. Once you know the basic concept, then you can understand any tough book or any standard books, so that understanding will be easy. First, basics must be clear. So here, this is the need. Bit 1 means what, sir? Some high voltage for a duration of TV. Whenever this high voltage is transmitted through this channel, what will happen, sir? Noise will be affected to this. Now what we must decide, we are transmitting two information, either bit 1 or 0. How the receiver will know 1 or 0 is affected? As it is varying, there is a threshold voltage 0 and 5 volts, and that is where the threshold is what? 2.5 volts. So comparator threshold is what? 2.5 volts. Whenever the input to this threshold, input to this comparator is greater than 2.5, it is treated as bit 1. Whenever the input is less than 2.5, it is treated as bit 0. So see here, bit 1 is represented with what? Plus 5 volts, and bit 0 is represented by what? 0 volts. This is a type of encoding. So every bit will be existing for a duration, that is called bit duration, rectangular form, constant voltage for a duration of TB. As soon as the signal received here is 1, 1, so here threshold will be generating those 1 and 1. What decoder will be having? Decoder will be having the same table which encoding is done. So what it will do? It will check this 1, 1. 1, 1 is mapped towards our 4 volts. So what it will do? It will just generate this 4 volts here. Because 1, 1 is mapped to 4 volts. The table it is having. So next, what is the information you will get, sir? 1, 0. As soon as 1, 0 comes here, the decoder will be mapping it to what? 3 volts. As soon as 0, 1 comes here, the decoder will be mapping it to 2 volts. And similarly, when 0, 0 comes, it will be mapping it to 1 volt. Now what will happen? The low pass filter will be integrating all these voltages. So what you will get? You will get the information like this. Whatever information is transmitted, V of t, that is received here. Clear? Any doubts in this diagram? Please let me clear. ये voltage कैसे निकले है? So answer for above questions are good. See, these voltages are encoding will map these voltages. Okay. See, whenever I'm speaking in a mic, what mic will be having? Mic will be having some valence electrons which are lightly bound. So whenever I'm speaking, these valence electrons will become free and they'll travel. And as we know, whenever a charge travels from one point to another point, voltage will be generated. So like that, whenever this person starts speaking, this mic will be having some free electrons. Those will be started moving, and what will happen? Voltage will be generated. So when I'm speaking loudly, more amount of voltage is produced because more electrons becomes free. And when I'm taking slowly, then less voltage will be produced. So this is how voltage will be produced. Okay. Clear, Manu Pandey? So any doubt in this diagram? Shall we go further? Please respond. Good. See here, the main aim of communication is what? Very simple. This voltage has to be received here because this person is waiting to hear. This is a half duplex one-way communication. Okay, but we have designed this circuit. Now this person is, so what we are thinking? We are thinking that he will receive the information and all. Whenever we are implementing this, na, so practically it is not happening. So this person is sat here. He is not getting any signal. All the values are zeros only. So can anyone tell me why we are not getting any signal here? When we implement, why we are not getting any signal at the output? Good. So my question is very clear, na? This is an idea. As an engineer, we have just manipulated the idea. We have just taken these blocks. We have encoded. But whenever we are implementing it practically, we are getting nothing here. The circuit is a failure. Why? Why we are not getting anything? Please share your views because you will also be future engineers. So whenever output is not coming, you have to think. Okay, that's how. So engineers will be building the blocks. Data loss or corrupted. Very good. So data loss is very good. Corruption in wide communication, the scope of corruption is very less. Okay. Data loss. Why data loss will happen, Saurabh? Why data loss will happen? Because of, if it is wireless, whenever signal is transmitting through air, so there is a possibility that data loss will happen. But this is wired, na? So what is the factor of data loss? Due to noise. Very good, very good, very good. See, whenever you are transmitting this voltage, na, this is a wire of some meters or kilometers. This 5 volts, you might have studied in electromagnetic theory. Every wire will be having what? Distributed lump networks, distributed elements, distributed resistance, distributed capacitance. What they will be doing? So whenever 5 volts is transmitted here, after some distance, there will be a loss. Okay, it will be 4 volts only. After some distance, there will be a loss. After some distance, there will be a loss. As the distance propagates, na, so you'll be getting all zeros only. You won't be getting any information. Clear? Due to noise. Very good. The problem here is due to path loss. So noise is somewhat different and path loss is something like signal attenuation. Okay. So here signal will be attenuated. What you have to do? What is the solution for this? Very simple. You have to use RR. Can anyone tell me what is RR? We have to use RR. What is meant by RR? So RR means regenerative repeater. It is something like a booster. Regenerative repeater. Sir, how many RRs we require? It depends on the distance between the transmitter and receiver, how much far they are. And it also depends on the what is the type of cable you are using. If you are using a cheap, less cost cable, so you must need more RRs. So RR is very simple. It will be placed whenever 5 volts is lost. Whenever there is a loss, if it is 3 volts, this regenerative repeater will boost it to again 5 volts. So again 5 volts will come here. Whenever it is 3 volts, again it will be boosted. Again it will be boosted. Again it will be boosted. So based on these RRs, what you will be getting? You will be getting the bit 1 and 0 here. Clear? Very good. Repeater is correct. Regenerative repeater. Nice. Nice. So sampler, we all know in signals we have studied the sampling theorem. Sampler, what is the condition of sampling? The sampling has to be done greater than or equal to what? Twice the 2FM. Twice the FM. Then only we can reconstruct the sampled signal from its samples. Okay. So we'll be focusing more on quantizer communication. So the next topic is quantizer. We'll be discussing about each and every block in detail. And in this link, you can get all the PDFs, all the gate questions where I have made a PDF. There are some 8 to 10 questions in that, so that you can just go through those questions while we'll be solving first. Okay, this is the basic idea. Are we clear here? Clear? Shall we move further? Hmm? Shall we move further? Good, good. So now we are going to discuss about quantizer, how a quantizer will happen. Here I have told you, na, whenever 4.2 is there, it has converted to 4. Whenever 3.8 is there, it is converted to 4. Something like that. Some basic idea I have told. But if you want to design it now, you must be very clear about what is the quantizer doing. Okay. So we'll be discussing about the quantizer now. Quantizer. So just to understand, we'll start with a basic example, and I'll be telling you how the quantizer is working. Okay. So let us think that the input is varying from 0 to 8 volts. 0, 2, 4, 6, and 8. I have converted them to some equal duration blocks, and for every block there will be a level, quantization level. Here the quantization level is 1 volt. Here the level is 3 volts. Here the level is 5 volts, and here the level is 7 volts. These are called what? These are called quantization levels. Okay. So your input is something like this, na? Input is varying from 0 to 8 volts. So whenever this input lies between 0 to 2 volts, na, it is quantized to 1 volt. Whenever input is lying between 4 to 6 volts, it is quantized to 5 volts. So once levels are made, then what you have to do? When the block diagram comes encoder, what encoder will be doing? It will be converting it to 0 0 0 1 1 0 1 1, something like that. Okay. So we are giving sampled values. After sampling, we have used quantizer. Na? So sample will be giving a constant sample, constant amplitude. That amplitude will fall in this duration because input is varying from 0 to 8 volts only. That is, message is varying from 0 to 8 volts. Message is varying from 0 to 8 volts only. So now tell me, sampler and quantizer and encoder. So please tell me any value, any random value. So I'll be telling you one example. Whenever input is something like 2.3 volts. So 2.3 volts is the input sample value to the quantizer. So quantizer, what it will be doing? It will be checking this value with this table. So 2.3 is lying somewhere here now. So this is from 2 to 4 volts. It is quantized to what? 3 volts, and it is encoded to what? 1 0. Yes or no? Sample to 2.3, quantized to 3 volts, and encoded to 1 0. So please tell me any voltage, any random voltage which is lying from 0 to 8 volts. Any voltage value which is lying from 0 to 8 volts. Please interact. Please tell me any voltage value between 0 to 8 volts. 6.6, 7.7. Very good. I got two values, 6.6 and 7.7. See here, 6.6 is somewhere here, na? So it is lying in this block. So 6.6 will be converted to what? Will be converted to 7 volts. And what is the encoded value of this one? 0 0. So another value is 7.7. So 7.7 is lying somewhere here, na? So what you will be getting? 7.7 is encoded to what? 7 volts. That is 0 0. There's one more example, 5.9. Very good, 5.9. So 5.9 is lying somewhere here, na? So what will happen? 5.9 is quantized to 5 volts, which is 0, 1. So now can you tell me when the input is 4 volts? When the input is 4 volts, what is the quantized value and what is the encoded value? So now the input is 4 volts here. What is the quantized value and what is the encoded value? 7.9 max value. Okay. 8 can also happen, na? Input is ranging from 0 to 8 volts. Then 8 is, Manu Pandey has told 4 volts only. See, 4 volts is not a quantization level, na? What are the quantization levels? Only 4 levels are there. Whenever input falls in this region, so quantizer can give only one of these 4 levels. So my question is, when the sampled value is 4 volts, what will be the quantized value and what will be the encoded value? 5 volts, very good. So what he is telling is, Saurabh is telling that this value is 5 volts and is encoded to 0, 1. See, whenever 4 volts is there, you can encode it to 5 volts or 3 volts. Yes or no? Because it is equidistant for both of them, na? So based on the designer, if I am a good designer, na, I'll be encoding it to the lowest value. Why? Less voltage, na? Understood? 7 volts, 4 volts is equidistant from both of them. But I'll be quantizing it to 3 volts only because less voltage, na? Yes or no? So if you if you quantize it to 5 volts, the voltage is more, investment is more. So whenever you are quantizing it to 3 volts, less voltage. That's what you have to do, optimization. Understood? So you can do this one also. That's also correct if you give the same information at the receiver. But the efficient one is if this is 3 volts and it can be encoded to what? 1, 0. Understood, students? So this is what some idea of how sampled value is converted to encoder, and we know that encoder is transmitting. Now let's see some mathematics, how questions are asked. So basically up to here what we have discussed are just ideas. Yes or no? Ideas don't give us marks. Ideas helps to understand the subject. But what gives us marks is mathematics. So let's do the mathematical analysis of this concept. Okay. The first formula is number of quantization levels. So number of levels depends on what? Number of levels depends on number of bits you can accommodate. So if you want more accuracy, na, if you want more accuracy, you'll be converting it to smaller number of logs, smaller number of levels. It means large levels you will have, smaller gap you will be using. So here, whenever you are encoding 2 volts to 1 volt, there is an error, na? Number of transmitted comparator. Role of threshold comparator. I told you, na, whenever noise is affected, so one of the student has asked the question, what is the role of threshold comparator? So whenever signal is affected by noise, what we are going to do? We are transmitting 2 bits, either bit 1 or bit 0. So whenever bit 1 is received or bit 0 is received, directly we can tell. But this bit 1 and 0 will be affected by noise. So these are varying ones. So what threshold comparator will do? It will have a threshold. If bit 1 is 5 volts and bit 0 is 0 volts, it will be having a threshold of 2.5 volts. What it will do? It will compare the input voltage with the threshold. Whenever input voltage is greater than threshold, it will give bit 1. Whenever input value voltage is less than threshold, it will give bit 0. So threshold comparator is nothing but what? Generator of ones and zeros at the receiver. Clear? Are we clear? Hmm? Please respond. Okay, we'll forward. So number of levels depends on number of bits you have. If you want to contribute only one bit, you have only two levels. Good, good. Okay, okay. Just focus on the present thing. Okay, focus on the present thing. You give your best to understand and ask whatever doubts you have. Clear? So number of quantitation levels is depending on what number of bits you can accommodate. If you can transmit only one bit for sample, that bit can be either 1 or 0. Only two levels we have, right? If you can transmit 2 bits per sample, you can be having 4 values. 2 square 4 na. So number of quantitation levels, these levels are depending on what number of bits you are transmitting per sample. Encoder is converting them to 0, 0, 0, 1, 1, 0, 1, 1. Based on what, sir? Based on because you are transmitting only 2 bits per sample. Clear? So the next one is step size. Step size means this value, this step. So this voltage is increasing with respect to step now. See here, this is a quantization level. If you add 2 volts to this, what you will get? You will be getting 3 volts. If you add 2 volts to this, you will be getting 5 volts. If you add 2 volts to this, you are getting 7 volts. So the step size here is what, sir? Step size here is 2 volts. The levels are increasing in the form of what? Steps, uniform. So what is the step size formula here? How you got 2? Can I write it like 8 minus 0 by number of levels? 8 minus 0 by 4. 8 minus 0 by 4, that is nothing but what? That is nothing but V max minus V min divided by level. If you are having 4 now, if you are having 4 levels, you can chop this into 4 regions. That is 8 by 4. That is how you got this 2 volts as step size. So what is the error you are getting? See here, in the process of quantizing, what we are doing, sir? In the process of quantizing, we are converting some 2 volts to 1 volt or some 4.2 volts to 3 volts. So what we are doing, we are rounding off the value. So that gives an error now. Actual value is, the sampled value is 4.2 or 2.9. But what we are sending? We are sending 432 something like that. So this will give you what? This will give you an error. So that error is called what? Quantization error. That error is called quantization error. So can you tell me what is the quantization error? It is nothing but sampled value, the actual value minus quantized value. Minus quantized value. What is the maximum quantization error, sir? Maximum quantization error. Can anyone tell me what is the maximum error in this example? What is the maximum error in this example? What is the maximum error, sir, in this example? Good. Good. Sampled minus quantized value. Good, Hemant. 4 volt. How 4 volts is the error? See here. Whenever 2 volts is there and 2 volts is quantized to 1 volt, it means what is the error, sir? 1 volt, na? Yes or no? So whenever 2.1 is there, 2.1, it is quantized to 3 volts. And the error is what? Minus 0.9. Whenever value is 2.9, when it is quantized to 3, what is the error, sir? 0.9. Sorry, 2.9 won't come here, no? So it will be 3.9. So what is the maximum error in this case? What is the maximum error? Please try to relate. See, 2 volts is the sampled value. Now what we are doing? Very good. 2 volts is the sampled value. What we are doing? We are rounding off it to 1 volt. Now it means we are introducing error of 1 volt. Whenever 2.1 is there, it will go to the next one. The error is minus 0.9. So it is less. Now. So maximum error happens here. 2 and 1. So the maximum error is what? Half of step size. Delta by 2. Delta by 2 is the maximum error. So what is the minimum error? What is the minimum error here? Minimum error. Please respond. What is the minimum error? No idea? Okay. Whenever 2 volts is quantized to 1, that is a positive voltage, positive error. Whenever 0 is quantized to 1, no, whenever 0 is quantized to 1, sampled value minus quantized value. There you will get the minimum error. That is what? So the range of error varies from where to where, sir? Minus delta by 2 to plus delta by 2. Whatever value lies here, the sampled value, na, this will be quantized to this voltage. In that case, error is positive. Whenever values lies here, if these are, whenever values lies between 0 to 1, they are quantized to 1 means what will happen, sir? So their error is negative. So the maximum error happens when 2 volts is quantized to 1. Maximum error is 1 volt in positive direction and 0 is quantized to 1 volt. The minimum error is minus delta by 2. So all these errors lies in the range of what? Minus delta by 2 to plus delta by 2. And there is one more thing. Okay. So these four are important. There are two more important mathematical analysis. Very good. Very good. Hemant, very good. Minus del by 2 to plus del by 2. Students, listen here. Now the fifth important point is coming here. That is bit duration. All bits are of equal duration size. So bit duration TB equal to what? Bit duration TB. See, whenever signal is converted to samples, na, sample will be somewhere here 4, 3, something like that. This is TS, 2TS. What you are going to do? 4 is converted to 2 bits, something like 1 and 0. Yes or no? 4 is converted to two values, 1 and 0. This is the bit duration, na? Yes or no? The overall time is what? The overall time is sampling time, that is TS. In this sampling time, what is the bit duration, sir? This is sample is converted to 1 and 0. 1 will be having a duration of TB and 0 will be having a duration of TB. So what is this TB? Can I write this TB as TS by 2? Because only 2 bits are there, na? Every bit will be taking half the time. That is why it is TB equal to TS by 2. In general, what is the formula, sir? TB equal to TS by N. If every sample is converted to N number of bits, it means the bit duration TB is what? TS by N. Clear? So then comes bit rate. Sixth one. Bit rate or bit speed. This is the most important one. So bit rate is nothing but what? Is inversely proportional to time. When the bit time is of more duration, the speed of the bit is slow. Whenever bit time is of less duration, the speed of bit is high. Less time means more number of bits you can receive, na? So this will be what? So N by TS. This is nothing but N into Fs. It is nothing but RB equal to N into Fs. Clear? So all of you please go through this link and download the PDF which is there. Then we'll be starting with solving the questions. Okay? Clear? So just go through the questions. So please download it in 5 minutes. We'll start with the question. And then we'll be seeing very important point, that is quantization noise. Quantization noise or quantization error. Let us consider message m of t equal to am cos 2 pi fmt. Then what will be the message power or signal power, sir? What is the power of am cos 2 pi fmt? What is the power of am cos 2 pi fmt? What is the signal power? Signal power equal to am square by 2, maximum value whole square by 2. Okay. So now what will be the quantization noise, sir? Quantization noise power. Because of quantization there is an error, na? That error will have a power, and that error is what? Is random. It will be changing randomly. So that is why we'll be using probability, error square. Mean square value is nothing but power. We all know power is nothing but what? RMS value whole square, na? RMS value whole square. What is R? Root mean square whole square. That is what? Mean square value. So mean square value is nothing but what? Mean square value is nothing but the power of the signal. Clear? So please go through that link. No. Go through this link to download the questions. Okay. So that is why power is nothing but mean square value. And we know expectation of x means what? Integration of x into f of x dx from probability x into f of x dx. What is the PDF of noise? The quantization noise is varying from where to where, sir? Is varying from minus delta by 2 to delta by 2. And it is uniform. Why it is uniform? Because every value can happen with equal probability. Every value, every sample can happen with equal probability. That is why all the values are of equal. And we know that the area under PDF must be 1. So this is a rectangle. If it is having delta, what must be this one, sir? This must be 1 by delta. Students, are you following? Please respond. Are you following? Can we move further? Have you got the PDF? Please respond. Yes, good. See here, E square into F error of PDF of error. The error is varying from minus delta by 2 to delta by 2, na quantization error. Good. So what you must get? You will get minus delta by 2 to delta by 2 E square, and error is uniform. All values is of equal probability. 1 by delta D. So this if you just calculate this, 1 by delta will come out. Integration of x square is x cube by 3. So if you substitute the upper and lower limits, you will be getting delta square by 12. And every statement in this is a formula. Okay, in some questions you can see in that PDF, some questions he will be asking what is the noise power. In some questions he will be asking what is SNR. So whenever you are transmitting a signal, noise is happened because of quantization, error is happened because of quantization. So if you want to check the performance of the system, now what we need? We need SNR value. So signal is there, error is there. To compare both of them, we need the SNR value. And what is the SNR value here? SNR is nothing but XQNR. This is not the normal SNR. The noise is because of what? Quantization. So that is why heading quantization noise. Signal power is AM square by 2. And what is noise power, sir? 1 by noise power you must need, na? SQNR is nothing but signal power by noise power. What is signal power you got? AM square by 2. And what is the noise power you got, sir, here? What is the noise power you got here? See here. Noise power equal to delta square by 12. Yes or no? So 1 by noise power means what you will get? Into 12 by delta square. What is delta? So we know na from the second characteristics, delta equal to Vmax minus Vmin by 2 power n. Second formula in mathematical analysis, the second formula of delta is this one. And for sinusoidal signal, what is the maximum voltage, sir? AM. And what is the minimum voltage? Minus AM by 2 power n. So what you will get here? 6 AM square into 1 by delta, na? That implies 2 power n divided by 2 into Vm, sorry, 2 into AM whole square. AM square will be cancelled. So you will be getting 3 by 2 into 2 ki power 2n. So this is the important formula for what? SQNR. That is what? 3 by 2 into 2 ki power 2n. So if you know these formulas, now directly within one step, you can solve all the questions. See, because of quantization, there is a noise introduced. That noise is nothing but quantization noise. What is the performance of that? SQNR equal to 3 by 2 into 2 to power 2n. And what is the noise power, sir? The quantization signal is varying from minus delta by 2 to delta by 2. So that is why if you find the mean square value, you will be getting what? Noise power. That is delta square by 12. So please write these two formulae. Okay. So have you downloaded the PDF? Have you gone through the questions? Please try the first question. Please students, have you downloaded the PDF? See, go through this link bit.ly slash 348 EAJ2. E is capital letter. Okay, in Google, if you just type, you will get that. Did you get the PDF? Yes or no? Please respond. Good. So remaining students, please get the PDF so that we can move further for solving those questions. You got the PDF now? Just try the first question. So let me write the conclusions here. Okay. Noise power is what? Delta square by 12. And what is SQNR, sir? SQNR is 3 by 2 into 2 to power 2n. So sometimes he'll be asking signal to quantization noise ratio in the form of dB. Whenever SNR value you want to find, na, so you have to take it as 10 log. 10 log 3 by 2 into 2 to the power 2n. So you'll be getting this one as 1.8 plus 6n dB. So these are the formulas which we have to remember to solve the questions. The mathematical analysis which we have given in the starting, na, sum 4 plus 2, 6 points we have seen: bit rate and step size, number of quantization levels, sampling and all. Clear? So that one table and this table, these two are enough to solve the questions in the PDF. Clear? Shall we move further? Try the first question. You got 2 minutes. Just try the first question and tell me the answer. So the formula which is needed, the hint which is needed to solve the first question is, see, 1 into cos omega t plus 1 into sin omega t. Please students, all of you go through this Google link bit.ly slash 348 capital EAJ2. Go through that link and download the PDF. Okay. So the hint required to solve the first question is, see here. Yeah, 1 into cos omega t plus 1 into sin omega t. So the formula is, you can adjust root 2 here. 1 by root 2. Please 1 minute. 1 by root 2 cos omega t plus 1 by root 2 sin omega t. So what you will be getting? Root 2 into cos of omega t plus 45 degrees or minus 45 degrees. Can I write it like this? Cos A, cos B, cos 45 is 1 by root 2 plus sin A, sin 45 is 1 by root 2. What is the maximum value of the input, sir? V max is root 2. And what is the minimum value? Minus root 2. We know cos value is 1 and minus 1. So as there is a value of root 2, you will be getting this V max and V minimum as. This is the hint required to solve the first question. You got 2 minutes. Just try the first question so that we'll discuss. Okay. Just try the question. Once you know n, once you know fs, what will happen? Very good, very good. So Ankita got 200, which is very correct. See, very simple. The question he has given, the signal is sampled at Nyquist rate, that is 2 into FM. What is the maximum frequency, sir? The signal is having two frequencies, na? One is 100, another is also 100. So 2 into 50, the sampling frequency is 100. And to get the bit rate, bits per second, bit rate, what is the formula for bit rate? The fourth formula which we have discussed, RB equal to N into Fs, na? Fs he has directly given as 100. What you need N. But he did not directly give N, he has given delta. By using delta, what you can find? You can find N equal to 2. So that is 2 into 100, that is what? 200 bits per second. Clear? Very good, Ankita, very good. So remaining students, did you understand? Have you applied the concept? Please respond. Have you applied the concept? Clear or not? So am I audible now? Yes. Very good. What about remaining students? Please take a pen and paper and just try solving them. What about remaining students? Did you get the logic? See, this is the signal which is given. Omega he has given as what? 200 pi. Both 200, sorry, 100 pi he has given. But the value V max is something like root 2. That's what the hint I have given. So if delta is given, you can directly get n equal to 2. Clear? Remaining students. Shall we go to question number 2? See, this is GATE 2015 question for 2 marks. Students, please respond. Students, please respond. See, GATE 2017. So 2015 is done now. The next question is a practice question. The next question is a practice question. So practice question you can just try. Okay. Tomorrow we have the same live at the same time. At 7 we have the live. So at the 7 we can try the practice question. You just go through that question and we'll discuss tomorrow. Okay. So what about the third question? An analog voltage is in the range, get 2014 one. Analog voltage in the range of 0 to 8 volts is divided into 16 equal intervals for conversion to 4-bit digital output. The maximum quantitation error is. What is the formula for maximum quantitation, sir? What is the formula for maximum quantitation error? What is the formula for maximum quantitation error? The maximum quantitation error is the third formula in the mathematical analysis, which we have taken as what? Delta by 2. Yes or no? So in the question, what he is telling, the voltage is in the range of, it is also in the range of the example which we have taken, 0 to 8 volts, and the levels are 16. So what is the formula for delta, sir? Very simple. V max minus V min by number of levels. The second formula in the table. So V max is 8 minus V min is 0 by number of levels is 16. So it is 1 by 2. So what is the maximum value? 1 by 2 into delta, that is 1 by 2, that is 1 by 4. That is what? 0.25. Get 2014 question. The answer is 0.25. See, get 2017 question. Next question. Very good. 0.25 you got, na? See the next question, get 2017 question. The question is, a sinusoidal message signal is converted to a PCM signal using a uniform quantizer. The required signal to noise ratio at the output of quantizer. The SQNR required is what, sir? 40 dB. 40 decibels he require. 40 dB he require. At the output of quantizer is 40 dB. The minimum number of bits per sample needed to achieve the desired SQNR. So this is required now. What is the formula? 1.8 plus 6n dB. So apply it. 1.8 plus 6n equal to 40 dB. So what is the n you will get? So just calculate it using mathematics. You will be getting n as 6.36. It means you need number of bits as what? 7. If you take only 6 bits now, if you just take n equal to 6 bits, what is the SQNR you can provide, sir? 1.8 plus 6n. If n is 6, you can provide only 39.8 dB. If n is 6, you can provide only 39.8 dB, but the SQNR required is what? 40 dB. So to achieve this, 6 n equal to 6 is not sufficient, so you need to put it as 7 bits. Clear? Clear, na? 2017 question. See how much easy it is. Once you know the concept, na? Once you are good at concept, you can solve a number of questions. It's just application of that. So go for the next question. Make it fast, make it fast. Get 1995. Very easy question. No need of pen and paper. Just apply it. Tell me what is the answer. If the number of bits per sample in PCM is increased from n to n plus 1. If number of bits are increased to n plus 1, what is the increase or improvement in the SNR? If n bits are there, this is the SNR, na? If n bits are there, this is the SNR. If n plus 1 is there, then what is the SQNR, sir? 1.8 plus 6 into n plus 1, na? That is 1.8 plus 6n plus 6 dB. Previous SNR is this one. Whenever now n is changed to n plus 1, na, there is an increase in 6 dB in the SQNR. SQNR is increased by 6 dB, na? So SQNR how? See, signal power by quantized noise power. We have derived it, right? Very good. Ankita has got 6 dB. Number of bits are n. When number of bits are n, the SQNR is this one. When these are increased to n plus 1, the SNR is increased by what? The previous value is increased by 6 dB. Clear, Vikash? Vikash, is it clear? 6 dB, option B. Good, good. Keshav, good. See the next question. Get 2003. The question is a sinusoidal signal with peak-to-peak amplitude of 1.536. So what he has given? Peak-to-peak amplitude. It means what? Vmax minus Vmin he has given. Peak-to-peak means what, sir? Vmax minus Vmin. He has given as what? He has given it as 1.536. Then what he has given further? It is quantized into 128 levels. That implies levels equal to 128 or 126. 128. Then what he is asking? The quantized noise power. What is the quantized noise power, sir? Delta square by 12, na? So what is the noise power? Delta square by 12. That is 1 by 12 into, what is delta? Delta is Vmax minus Vmin divided by L. This is delta. There is a square, na? Put the square here. That is 1 by 12 into 1.536 divided by 128 whole square. Clear? So use calcium, just find its answer. You will be getting it approximately 12 into 10 power minus 6. 12 into 10 power minus 6. Any doubts in this? Please respond. Any doubts in this? So which is option C? Option C is the correct answer. Clear? Yes or no? So see the next question. See, next two are conceptual questions. Very simple. Just try to relate the concept. The question is, get 98 question. A signal having uniformly distributed amplitude in the interval minus V to V is to be encoded using PCM with uniform quantization. The signal to quantized noise ratio is determined by what? The signal to quantize noise ratio is determined by what? Tell me, sir, what is the answer for this? SQNR is determined by what? SQNR is determined by number of bits. In the given options, which is determining the number of bits, sir? Number of quantization levels. Based on levels, we'll be designing the number of bits. So the answer for that is what? Is option C, number of quantization levels. Very good, very good. Ankita, very good. See the last question. Please tell me what is the answer for the last question. What is the answer for the last question? The signal to quantize noise ratio in an n-bit PCM system. See the options. Increases depends upon the sampling frequency employed. Is it depending on sampling frequency? Sampling frequency means what? Fs na? It is not depending. Very good. She got C. Very good. Very good. Independent of the value of n. That's wrong na. SQNR is depending on the value of n. And see option C. It increases with increasing n. Correct only na. Whenever n increases by 1, SQNR increases by 6 dB. So when n is increasing, SQNR is increasing. The last option is what? Decreases with increasing the value of n. That's wrong. Why? Because these two are directly proportional na. Very good. Very good. Option C. Very good. So this completes the topic of PCM. If you want more questions on this, more questions to solve on this concept, you can strictly go through this our channel. So in this PDF, you are getting nearly 10 questions. Okay. If you want more questions, you can go through www. The same channel which you are watching, thegateacademy.com. There in the videos, search, there will be a search option. Search for digital communication first. There will be some questions tagged as digital communication or pulse code modulation. So these are only the two topics. Whenever search button is there, you can search the videos so that all the questions, all the gate questions, so which are there, so they will be coming to you. So whenever question is there, you just go through the question. Don't see the solution. Okay, video solution will be there. Don't go through the solution. Just see the question whenever I'm reading for 2 minutes or 3 minutes. So write down the question. Try to solve by applying the given formulas today. Try to solve them. Once you have the solution, then go through watching that video. Okay. So this must be relative. When you see a solution and you understand, there is nothing you are doing. Okay. If you have a solution on your own, then when you compare your solution with the actual solution, you'll come to know which one is better. If you are following the actual step of what I have done, so it's good. If you are doing some error where you are going through the error, you'll be understanding where you are doing the errors. Clear? Very good. Very good. Option C is correct. So this is about pulse code modulation. So this pulse code modulation has a drawback. Okay. What is the main drawback of the pulse code modulation? Can anyone tell me? Our idea of noise reduction is done, but this pulse code modulation has a drawback. What is the drawback? Please respond. What is the drawback of this pulse code modulation? Please respond, students. What is the drawback of pulse code modulation? No idea? Required more number of bits to transmit data. See, number of bits depends on encoding. Na? You can transmit them using more or less. If you use less number of bits, then your performance will be less, but transformer means signal transfer and reception is done. Yeah, that is also there, but comparatively, what is the more error in this? What we have discussed today. Okay, so the main error of this one is what? Quantization noise. In the process of quantization, noise is improved. Noise is inculcated in the signal. Na? This is the one, quantization noise. So whenever we are studying this noise, we have done the analysis of noise based on signal how noise is, that is the SNR value. But we did not do any steps to reduce this noise. So this noise is depending on what, sir? Maximum quantitation error is what? Delta by 2, na? So we are going to reduce this error in tomorrow's class. Okay. So we are going to reduce this delta. How effectively we can reduce? These all things we are going to discuss in tomorrow's class at the same time. Clear? Step size not steroid, very good. Drawback is depending on steroid quantitation noise, very good. Required more number of bits to transmit data. Clear? So how we can reduce the quantitation error? What is the benefits we are going to get? How the bandwidth is changing? These all stuff. What is the advantage of reducing this? How the circuit will change? These are very interesting things we are going to discuss in tomorrow's class at the same time, 7 to 8. Okay. So please download this PDF and go through these questions. Okay. Step size not steroid. Thank you, students. Keep the good work doing. Okay. Whenever a concept is there, make it into small breaks. Break it into small parts and focus on each and every part. Okay. That's the way of studying things. And whenever formulas are there, so you make a table. So in the today class, we have two tables. Okay. Basic ideas are able to understand the concept, but whenever you are going to solve a question, na, your mind in your mind you must be remembering the table. Okay, that's how time is saved in gate. Okay, all the best. So come tomorrow, we'll be going to discuss this stuff of reducing the quantization error. Thank you. Thank you.